All right, welcome. So now that we've been studying eigenvalues and eigenvectors, it's fair to ask, well, what is the point of finding eigenvalues and eigenvectors? And so one really nice property that we can show right now is that we can very quickly figure the eigenvalues for powers of matrices. So when I say a squared, this means a times a, and this only makes sense if we have a square n by n matrix. And so the first comment here is that if I know that lambda is an eigenvalue of matrix A, then let's show that lambda squared is going to be an eigenvalue for the matrix A times A. So if we take A squared times x, that's equivalent to taking matrix A times x. And since we're told that lambda is an eigenvalue of matrix A, that means AX is equivalent to multiplying vector x by scalar lambda. So I can replace AX with lambda x. And now this scalar lambda property of multiplication is that we can pull this out in front. So we can pull the lambda out in front of this product, and now what's left is lambda times AX. And then we can use this fact again, that lambda is an eigenvalue of matrix A. So that means this product AX is going to equal lambda x. So that gives us lambda times lambda x, or in other words, lambda squared x. And since we know that lambda is an eigenvalue, that means this x, there exists some non-trivial x for which this is true, then that means there exists some non-trivial vector x so that a squared x acts like lambda squared times x. So this tells us that lambda squared is an eigenvalue for a squared if we know lambda is an eigenvalue of a. And we can jump up to higher dimensions. For example, we can show that lambda cubed is an eigenvalue for a cubed, much the same way. We start with a cubed times x. We can write that as a times a squared x. And then we can use our previous result, that lambda squared is an eigenvalue for a squared. So a squared x is going to act just like multiplying by lambda squared. And now we can use the fact that we can pull out the scalar lambda squared out in front of this product. And we know that lambda is an eigenvalue for matrix A. So AX is going to equal lambda x. And that gives us one more power for lambda. So you can see how this is going to proceed. So we've got lambda cubed is now an eigenvalue for the matrix A cubed. And hopefully you've caught on to the pattern here that in general, if lambda is an eigenvalue for matrix A, then lambda to the k is going to be an eigenvalue for a to the k. Where here, we're thinking about exponentiating. So k is denoting 2, 3, 4, 5, 6. So these are positive integer values. And so this property is going to be really, really nice when we're working with what are called difference equations, or when we're working with any sort of Markov chain. And we'll encounter these applications later in this chapter. But this is going to be an extremely helpful time-saving result when we get to those examples.